All right. Looks like we're live again. All right. This time we're doing 2.4. Am I on the right thing? Okay. When we studied first order, all right, I'm not too familiar with this section, so we're going to read through this kind of slowly. But let's just look at what some of the problems are. I like to look at some of the problems before we even read the section, kind of. For the given functions, determine if y of t is a solution system. Oh, you know what? That's what was confusing me before. Okay. All right. Yeah. Earlier when I was like confused how we could have two systems with like e to the minus 2t, but it's because I wasn't plugging it into the system to understand its yeah. I, I don't know. Those seem like good problems though. Why should we immediately know that this is not? Because we can just integrate this like normal and this is not going to have a 2t in it. I think that's the answer, but I don't know. Although we can use the method described in this section to derive the general solution, isn't there an easier way to show that is a solution for e to the 2t minus e to the minus t3e? Okay, well that'll be interesting because I don't see why that is the case. Use the method described in this section to derive the general solution. Can you choose constants in the general solution obtained in exercise 7 that yield the function? Hmm. Using the result of exercise 7, determine the solution that satisfies the initial condition. Okay. In the xy plane, plot the solution. Determine the solution that satisfies the initial condition. Okay. Again. Determine the solution is okay. Another initial condition. That's kind of interesting. Plot it using sketch the. Okay, that's fine. Another wow, a lot of initial condition ones. 5 initial condition ones. 4, whatever. Okay, get the. Okay. This is not linear, so it's gonna be harder. I think there's only one equilibrium though. Because there's no, yeah. I think there's still only 0, 0. Oh, and that's it? Okay. So we should be able to bang this one out pretty quickly. If the reading is not too long. The reading does look a little long though. Okay. I'm gonna take a walk around the block. I'm gonna take a short break. I'm getting stir crazy up in here. Let me just do this. When we first studied first-order differential equations, we saw that we could sometimes derive a formula. When that happened, the analytic techniques for computing were especially adapted to the form of the differential equation. For systems of special forms for which we can apply analytic techniques to find explicit solutions are far and few between. They're few and far between. Because they're rare. These special systems are very valuable. We can use them to develop intuition, even wisdom, that we can then use when studying systems for which analytic techniques are unavailable. The most important class of systems that we can solve explicitly, the linear systems, is studied at length in Chapter 3. In this section, we discuss analytic techniques that apply to very special classes of systems. Use the formulas that we obtain become more familiar with. All right, checking solution. As noted above, finding formulas for a solution of a system can range from difficult to impossible. However, once we have the formulas, checking that they give a solution is not so bad. I need some natural light. I'm going to open up the... Oh, it's so much better. All right. Many of the techniques are sophisticated guessing schemes. Once we make a guess, we can test to see if our guess is actually a solution. We can rewrite the system in vector notation. I suppose. All right. Suppose that someone hands us a solution, then we can just evaluate and check. Hmm. To check that y of t satisfies the initial condition, we evaluate it at t equals to 0. Next, we see if the first equation of the system is satisfied. -5 and -3. Okay, so that's not good. Decoupled systems. One of the things that makes systems of a differential equation so difficult and interesting is that the rate of change of each of the dependent variables often depends on the values of other dependent variables. However, sometimes there's not too much independence among the variables. Interdependence among the variables. In that case, we can often derive the general solution, chapter 1. All right, so we call it completely decoupled when the incidence matrix is diagonal, effectively. The dependent variable equation matrix is diagonal. The general solution is two underdetermined constants. To just any additional condition, right? Okay. Okay. Partially decoupled. For this system, the rate of change of x depends on both x and y, but the rate of change of y depends only on y. We say this is partially decoupled. Okay. Oh, I actually kind of, now that we're doing this, I kind of like how this has been introduced. That's pretty interesting. Wait. Let me get this right. So, minus 6a to the 3k, okay, 2, then you get alpha. And alpha, what? So this is using the guess method of solving for the homogeneous part. But wait, why is this 2t? Oh, they do this to find xp of t. Oh, yeah, okay. So first they find, I usually do it the other way. First I find the homogeneous, then I find the particular. But first they found the particular, and then they're just like, look, it's dx dt is equal to 2x, so that's clearly k1 e to the 2t. But what is k2? Okay. Okay, there we go. That's the full solution. All right, that makes sense. That wasn't that hard, but it did take a second. Okay. They keep teasing this, man, that the solution curve lies on a line. Oh wait, there we go. Okay, yeah, hold on. I didn't read as much as I should have. Um. Oh, interesting. Okay, that's another way of thinking of it. I didn't think about it like that. Since the ratio of y over x is constant, the solution curve lies on a line through the origin in the phase plane. The fact that this system has a solution curve that lies on a line is an artifact of the simple algebra of the equations. This sort of special geometry will be exploited extensively. All right, cool. That was easy. All right, so let's hop into some problems. Okay, so we're just trying to check if this is a solution. So the first thing we're going to do is we're going to take x prime is equal to y prime so then we're going to get this is equal to 4e to the t minus 2e to the t is equal to 2e to the t minus 3e to the t. Check, check. Okay, one is yes. So this is going to be 2 times, oh wait, but this is x prime. So this is going to be 2 times x, which is 4e to the t minus 2e to the 4t. Dude, why am I doing this? This is so boring. This is so boring. And this is going to be plus minus 2e to the t plus 2e to the 4t. Nope. Let me just double check my answer too. But I'm almost positive that that's not a solution. Yeah, it's not a solution. Okay, good. All right, problem 5. Although it's given a partially decoupled system. Okay, it's set 5 is easy. All right, 7. All right, 7 is give a general solution. So let's do general solution. All right. So y of t is clearly c. Or let's do k. I don't really know. K2 e to the minus t, right? Because if you do dy dt is equal to minus y, you get dy over y equals minus dt integral. You get ln of y is equal to minus t, and then you get plus c, then you get y is equal to e to the minus t plus c is equal to e to the c times e to the minus t is equal to k to e to the minus t. Okay. Next we go x dot minus 2x is equal to k2 e to the minus t. So we have sort of 2 methods to solve these linear non-homogeneous differential. Linear non-homogeneous differential equations. This is non-homogeneous because this is not. Anyways, we can either use integrating factors, where we multiply this whole thing by some u of t, such that u dot is equal to u times minus 2, or we can guess. So we're going to guess. I think we're going to guess because otherwise we'd have to take the integral of u of t k to e to the minus t, which is a hard integral because then you have to do a product. And I don't know if we want to do a product. So let's so the first thing is we're going to take, so x dot is equal to a of t y, x plus b of t. So we solve x h of t is equal to e to the 2t, c e to the 2t. But now we need to guess. Wait, I think I'm missing something because what if to guess this, you say let xp of t equal, some constant a times e to the minus t, and then you get x prime is equal to minus a to the e to the minus t. Then you get minus a e to the minus t minus 2a e to the minus t is equal to k2 e to the minus t. Now that you have this, you can rewrite this by factoring, and you can get minus 3a is equal to k2. A is equal to 1/3 k2. So then our particular solution is going to be xp of t is 1 minus 1/3 k2 e to the minus t. With that particular solution in mind, we can now do our whole solution. X of t is equal to let's say k1 e to the 2t minus 1/3 k2 e to the minus t. But that's, oh wait, let me do this. No, I think that's right. And then y of t is equal to k2 e to the minus t. And then that should be the general solution to the equation. How do you get good at it? You gotta practice. I'm not good at it either. Okay, but we should check if that's right. And no, I'm not gonna check. Put a shirt on. Why would I put a shirt on? It's hot as heck in here. Okay. Parth, if you tell me to put on a shirt again, I'm banning your ass. I'm banning it. All right, let me not really. All right, so we're going to just check if my solution is correct. So this was problem 9. Wait, what just happened? I just heard a weird sound. Is my camera still working? Oh, my camera disconnected somehow. Okay, well, I'll fix that in a second. Let's just check my K2 e to the, wait, whoa. You got to be careful. So what we did is, my solution doesn't look right, but it actually is, because I just switched K1 and K2, but that's fine. It's just a naming thing. But as long as this K1 and this K1 are this, or as long as this name and that name are the same, then we're good. Okay. Let me just fix this camera really quickly. Damn it. Damn it. Okay, hold on. But let's try this. Oh, there we go. All right. Okay, so let's get back to it. I don't know why it sometimes just like randomly disconnects. It's kind of annoying, actually. All right. What's next? What's next? Okay. Determine solution satisfy. This is 9. Y of 0 equal to 1, 0. Okay, so our differential equation solution was x of t is equal to y of t is equal to, I forget what it was. It was like k1 e to the 2t minus 1/3 k e to the minus t or something, k2, and then k2 e to the minus t or something. It's something like that. Let me just double check. Yeah, that's exactly right. Okay, so now we just need to check. So if we plug in for 0, we're going to get k1, so x of 0 equal to 0 equals k1 minus 1/3 and then so k2 has to be 1. Okay, so now we get k1 minus 1/3 is equal to 0. Really? K1 equals 1/3? So then our solution is minus, wait. This, oh wait, I got this wrong. This is 1, 0. K2 equals 0. So K1 equals 1. Is that right? So then that can't be right. Oh, you know what? That actually is right because that corresponds geometrically. Okay, so if you're at 1, 0, then y actually, since this term is yeah. Okay. So for this initial condition, y is going to be at 0, or right. So y prime of 0 is equal to 0. All right. So I'm pretty sure this is the case. So then what the behavior of the system is going to be is going to be x of t is equal to 1 e to the 2t. So that just corresponds to uh, going away from this equilibrium. Or wait. It's going to be going away from this equilibrium. So the solution curve just looks like this guy going along this way. Okay, we can skip 11. Okay, let's do 13. All right, 13 is find the general solution of x dot equals 2x minus 8y squared and y dot equals minus 3y. All right, so find the solution. No, I don't know what I'm doing. All right, so here we're going to get y of t is equal to k2 times e to the minus 3t. Then we can plug that in for x of t, and we're going to get x dot minus 2x is equal to minus 8 times k2 e to the minus 3t. Now what we can do is we can guess a particular solution, or we can guess a particular solution so that the left-hand side and the right-hand side are equal. So if we guess x of, let's call this xp of t is equal to a e to the minus 3t, then x dot p is equal to minus 3a e to the minus 3t. Then if we plug that in for here, we're going to get minus 3a e to the minus 3t minus 2a e to the minus 3t is equal to minus 8k to e to the minus 3t. All right, so now we can factor this out, and we're going to get minus 5a is equal to minus 8k2. So then we can write a in terms of k2. So we're going to get a is equal to 8/5 k2. Now we can go back up here and we can rewrite this as 8/5. Now that we have the particular solution, we need to find the general solution. Okay? Okay, so the general solution of this equation, we basically, to find the general solution, you only take the homogeneous part. You remove the affine part. So then we're going to get for xh of t is equal to e to the, or let's do this, k1 e to the 2t. Now our full solution is going to be x of t is equal to k1 e to the 2t plus our particular solution. Oh wait, but this is actually, yeah, this is where I messed up. This is 8/5 k2. The parameter is still in there. So this is going to be 8/5 k2 e to the minus 3t. So that is, I think that's everything, right? And then, so this whole thing is the general solution, but now we probably need to find a couple of initial condition solutions. Oh, okay, find the equilibrium points. All right, so the equilibrium points are actually pretty easy because the only way that this system is at equilibrium is if y dot equals 0, and if y dot equals 0, then implies that y is equal to 0. So now we just need to find points where if y is 0 and x dot is going to be equal to 2x, but for this to be 0 implies that x is equal to 0. So the equilibrium solution is, so we could, how do we want to write this? big Y of t is equal to 0, 0 is equilibrium solution. All right. All right, now it says find y0 equal to find solution such that the initial condition is 0, 1. All right, so what that means is that we're going to plug in t equal to 0 for these expressions, which is going to give us x of 0 equals 0 k1 plus 8/5 k2, and y of 0 is equal to 1 is equal to k2. So k2 equals 1, so then we're going to get k1 equals minus 8/5. K2 equals 1. All right, we can double check our answers. But I'm pretty sure that's correct. Okay, let's just double check and then we can move on. Did I switch it over? Okay. 2.413. Let's see. Find the equilibrium solutions. That was correct. Let's see. K1 e to the 2t plus 8. Oh, interesting. Okay, we got this wrong actually. We need to go back and figure that out because that doesn't make sense. We got K2 squared. How did that happen? Okay. Okay, we need to figure that out because I don't know how they got that. And then K2 e to the minus 3t. That was all good. That was easy. That was immediate. Oh man, we really messed up the C as well. Okay. How did they get K2 squared? Okay, how did they get K2 squared? We guessed 3a for our solution. Or we guessed guess a e to the minus 3t. And then we got minus 3a to the, and then we plugged in oh wait, you know what? This y squared might have been it. Oh, the y squared was the whole thing. I totally missed this. Okay, so the problem here was that while we solved this, this needed to be squared. So then we got K2 squared, and then this should be, I think, minus 6, right? Because if we had, so then, oh, so we needed to guess minus 6 here. So minus 6. And this all this stuff got messed up. I don't know. All right. should we do it again, or should we just be like, all right, you know what? Let's do it again. Why not? Okay, so let's just start from here and all right, so let's just fix this. So we get minus 8 k2 squared e to the minus 6t is equal to x dot minus 2x. So our homogeneous solution x sub h is correct. You guys are funny. Okay, so what do we need to do? We need to guess. So we guess xp of t is equal to a e to the minus 6t this time. Then we get xp dot is equal to minus 6a e to the minus 6t. So then we get this minus 6a e to the minus 6t minus, plus, this is going to be 2. This is going to be 12a to the ae to the minus 6t is equal to minus 8k2 squared e to the minus 6t. All right, so we get 6a is equal to minus 8k2 squared. So then we should get a is equal to 4/3 k2 squared. So then our particular solution becomes not that. So then it becomes 4/3 k2 squared e to the minus 6t. So then we just need to sum them. So we need to take their sum. So we get x of t is equal to k1 e to the 2t plus 4/3 k2 squared e to the minus 6t. Okay, and then what did we say was the guess for the initial condition we need to figure out is the equilibrium points stay the same. That's fine. It's still 0, 0. But then we need to find the x0, y0 equal to 0, 1. So I think in that case 0, 1. Wait, 0, 1. Okay, fine. So we get this. Okay, so we get x of 0 is equal to 0 is equal to k1 plus 4/3 k2 squared. And then x or y 0 equal to 1 is equal to k2 e to the minus 3t. But this goes away. So then it's k2. So k2 equals 1. Yeah, let's see if that was correct. You're from Ireland? Damn, bro, that's sick. That's cool, man. All right. All right, so we got this finally. But you know what? That's kind of weird. It's like, wait, how did they see? I feel like they didn't. All right, let's see how ChatGPT does it. I just want to make sure that we have the the coefficient of the k is correct. Just make sure that we have the coefficients of the k is correct. Oh, it used an integrating factor, bro? What the hell? I'm just trying to figure out where that 4/3 comes from. And then x0. Okay, so yeah, so we need to be careful because this is c1 squared minus 6t c2. Okay, that's fine, but the xp was 4/3 k squared e to the minus 6t, but the book doesn't. You're a math major? That's sick, dude. That's so cool. Math majors are badass. Oh my goodness. Wait. Oh, you know what happened? Okay, yeah, so I plugged in the derivative. To instead of the yeah, so this just needed to be 2a. Okay. 2a. So then you get minus 4. Wait. Why is it minus? Oh, it is minus. Oh, because you don't take the derivative. Oh. You got to be really careful about those. Yeah. So a is just equal to c. Okay. All right. Cool. Let's see. Is there any others? Okay. So wait. Let's see. Let's just read through this. Yeah, it's just changing scalars to vectors. It's really not. Oh, but then they scalarize it. That's fine. I mean, it's fine. All right, I just want to see. I mean, I don't really know if I want to like. Use Euler's method. Use Euler's method. The points on the solution curve are one is. They diverge eventually. Check it, simulate it, discuss. Okay, it's all simulation, right? So I might skip this section and we're just going to jump to 2.6. This line corresponds to one of the eigenvectors. But if there so if there is a real valued eigenvector, then at least one of them travels on a straight line. But if the other one is complex, then it's not going to be on a straight line. Okay. So all of this was just simulate Euler's method. All right, so we can jump onto this section. I do like to split up the streams. Let's see. This one only took an hour. Actually, that's kind of amazing that the and 10 minutes of that was just me on a break. All right, so we're going to do 2.6 then, which is an important section because it's existence and uniqueness. There's almost certainly going to be a question on this on my quiz. All right. All right, so let's just end the stream and then we'll hop back on.